Hello everyone. In this lecture we are going to discuss about some properties of the Root-Locus which will help us in drawing the Root-Locus for a given system. We'll go through a number of the rules and we will do it one by one. So the first one to consider is called as rule number 0, and it tells us that the Root-Locus is symmetrical with respect to the real axis. So when we want to draw the Root-Locus, we will draw it in the S-plane where we have the real axis and the imaginary axis. This rule tells us that the Root-Locus will be symmetric with respect to the real axis. It should be kind of obvious because the Root-Locus shows us the location of the closed loop pose of the system. And you should know that for the real systems that we consider, if we have the poles are either real valued or they have complex value. If we have a pole with a complex value, then we have another pole which has the same real value, but for the imaginary value the sign is different. Okay, so we have indeed the complex conjugate of a complex pole. If we have one pole here, then for sure we have another pole over here as well. And since the Root-Locus is going to show us the location of the closed loop pose of the system, when we draw the Root-Locus, if this is part of the Root-Locus, then we will have the part of the Root-Locus which is symmetric of this one in respect to the real axis. So that's something that you should always keep in mind. The next rule is regarding the number of the branches that we have for the Root-Locus. In general, we will have, if we have n number of the poles for our system, if we have n poles and m zeros, our Root-Locus will have 2 times n number of branches, where n of them will be in the positive locus and n of them will be in the negative locus. And usually we will draw the negative locus and positive locus separately. So for each Root-Locus that we draw, there will be n number of the branches. N number of branch for positive locus, n number of branches for the negative locus, and in total there will be 2 times n number of branches. It's also quite straightforward to understand why this is the case. We know that the characteristics equation that we have for our system is in the form of d of s plus rho times n of s equal to 0. When we have a positive number for rho, or when we have a negative number for rho, there will be in it, we can say that we will have 2 polynomials of order n, and each one of them will have n number of the roots. So in each case there will be n roots, which will vary based on the value of the rho, and that means that we will have n number of branches for each case. So n branches for the positive locus and n branches for the negative locus. The next rule is regarding the origin and end of the branches. For both positive locus and negative locus, the n branches that we have will originate at the pose of the GP of S. And you should keep in mind that GP is indeed the controller GC times the process, where we have taken the gain out. Okay, so the pose, the branches will originate at the pose of the GP. M of them will terminate on the zeros of GP, and the remaining ones will go towards infinity. We will see later how these branches go towards the infinity. But keep in mind again that for our system we have n number of poles and m number of zeros. So out of, for each positive locus and negative locus, m branches will end at zeros, and the remaining n minus m branches will go towards infinity. And all of them will originate from the, let's say, open loop poles of the system, okay? Poles of GP of S. We can kind of prove this property by looking at the equation, the characteristics equation that we have for the system. 1 plus rho times numerator over the denominator is equal to 0. We can rewrite it in the form of denominator s plus p1 times s plus p2 plus s times s plus pn plus rho times the numerator, which is equal to 0. When we say that the branches originate from somewhere, we mean that at that point rho is equal to 0, because we start the rho from 0 and then we approach the infinity. So when rho is set to 0, we can see that this part of the expression will vanish, and then the polynomial that we have will be in the form of s plus p1 times s plus p2 times s plus pn equal to 0, and we can see that already we have the poles of GP of S as the roots of that equation. Okay, so this means that the branches will originate from the poles of the open loop system. As rho approaches the infinity, when rho approaches the infinity, the second part of the equation will become dominant, and the first part over here could be neglected, okay, because rho is huge. So rho times something will be considered more dominant than the other part. And then if we set it to 0, we can see that this time Z1, Z2 up to Zm will be, with the negative sign, will be the roots of the polynomial. And as a result, since we have m number of them, as rho approaches infinity, m number of the branches will end up at those points. The remaining n minus m branches, which we denote as r as well, will end at infinity. Okay, so if we have more number of poles than the zeros, some of the branches will go towards infinity, and the remaining ones will end up at the zeros. But whenever we have that case, when we have more poles than the zeros and we have branches that go towards the infinity, these branches will approach the infinity using some asymptotes. So there will be some asymptotic behavior for the branches, and those asymptotes will meet on the real axis at some point, which we call as the point of abscissa. The point of abscissa could be found referring to this formula that we have. XA is equal to 1 over R, where R is equal to n minus m, times sum of zi's minus sum of pi's. You just need to keep in mind that we are using the representation for GP of S in this form. Okay, so at the numerator we have S plus Z1, S plus Z2, and so on and so forth. At the denominator we have S plus P1, S plus P2, S plus P3, and so on and so forth. So referring to the values of Zi and Pi's, we will have the point of abscissa calculated. These asymptotes will also form angles with the real axis. We call it as CA, and that could be found by referring to this formula. R times KCA will be equal to 2h plus 1 times pi for positive locus and 2h times pi for the negative locus, where h starts from 0 and it goes up to r minus 1. So it will depend on the number of the branches that we have. If we have, let's say, the number of the asymptotes, and if we have 3 asymptotes, then we will have h equal to 0, 1, and 2. How these results are obtained, we can have a look at the characteristics equation in this way. When s goes towards infinity, and of course rho goes towards infinity as well, so we will have the limit of rho times gp prime of s equal to limit of rho times, this is not needed here, s plus c1 times s plus c2 over the denominator, which is in the form of s plus p1 times s plus p2, and so on and so forth. And then this could be written in the form of limit of s going towards infinity, rho over s minus alpha to the power of r. This kind of means that we look at the, let's say, open loop poles and zeros of the system from very far. So when you look at all those poles and zeros from very far, it kind of looks like that they all are at a similar location, which we call as A. And this will be the point of, this will determine the point of abscissa for RCM. Over there, the asymptotes will be indeed meeting with the real axis. And obviously, if we want to find out xa, this will make sense only if we have r bigger than or equal to 2. Because if we have only, if r is equal to 1, this would mean that we have only one asymptote. And when we have only one asymptote, that asymptote will lie on the real axis. And when it lies on the real axis, the point of abscissa will not be important. It could be any point, yeah? If we are on the, if you want to draw, let's say, an asymptote on the real axis with the angle of 0, it doesn't matter whether we start from here, or we start from here, or we start from here. In all cases, the asymptote, which will be important when we approach the infinity, will be the same. So only when r is bigger than or equal to 2, we will be interested in finding the point of abscissa for our system. The next rule is regarding the root locus on the real axis. As a general rule, we should know that all the points on the real axis belong to the root locus. Some part of the real axis belongs to the positive locus, and some parts belong to the negative locus. How we should determine which part belongs to the positive locus and which parts belong to the negative locus. Regarding the positive locus, we need to count the total number of real poles plus the total number of real zeros to the right of the test point. So you pick a point on the real axis, you call it the test point, and then you need to count the total number of real poles and zeros to its right. So if this is the test point for me, I need to count the total number of poles and zeros on its right. If that number is an odd number, such as 1, 1, 3, and so on and so forth, then the test point will belong to our positive locus. So this test point will belong to our positive locus, and obviously until we have a pole or zero on the real axis, that part of the real axis will belong to our positive locus as well. So basically, when we consider the real axis, we will look at segments of the real axis, because for each segment, which is between poles and zeros, the total number of the poles and zeros on the right hand side will be the same. If the number of the poles and zeros to the right side of the test point is an even number, then that point, that segment, will belong to the negative locus. This just comes from by applying the phase condition, okay? So it's not something difficult to prove. You just apply the phase condition at any point, and based on the phase condition, whether it's for the positive locus or negative locus, you will see that if the total number of the poles and zeros to the right side is equal to an odd number, then that belongs to the positive locus, otherwise to the negative locus. We also count the number of the real poles and real zeros to the right side. We don't consider the complex ones in it, because if we have a complex pole, we will have the complex conjugate pole as well, and then the contribution that comes from those two poles will be equal to 2 pi, because if you can see it as an example over here. So if this is the test point, if I want to calculate or find out the contribution, the angle contribution from a pole, we draw the horizontal line towards plus infinity. We connect that pole to the test point, and then this will give us θ1. If I do it for the complex conjugate pole, we will get θ2, and you can see that θ1 plus θ2 will be equal to 2 pi. So we can indeed neglect these complex conjugate poles. Alright, so this way we can determine the part of the real axis that belongs to our positive locus or negative locus. Let me give you an example before moving forward to the next rules. Let's assume that here we have the poles and zeros. So 3 poles and 1 zero. I can consider this segment of the real axis, which is from the pole to plus infinity. If for any point on this segment we count the number of the poles and zeros to its right side, we will get the number which is equal to 0. And 0 is not an odd number, so this part will belong to the negative locus. Then we can move to the next segment, which is between this 0 and the pole over here. For any point on this segment, if I count the number of the poles and zeros, we will see that we have only this pole over here, and then the number will be equal to 1, which is an odd number, and therefore this part of the real axis will belong to our positive locus. The next segment to consider on the real axis is this segment, for which if I count the number of the real poles and zeros on the right side for any test point, we will get these 2 poles and zeros. So the number that we get over here will be equal to 2, which is an even number, and as a result, this segment of the real axis will belong to our negative locus. So we know that this belongs to negative locus, this part belongs to the negative locus, and the area between the 0 and the pole belongs to our positive locus. This will be quite useful in drawing our root locus for positive locus and negative locus later. Okay, so I think that's all for this video. In the next video, I will continue considering the other rules that we have for drawing the root locus. Thank you for watching.